Hey y'all, Miss Catalano here. First off, I want to remind you that unlike an in-person lesson, you can take advantage of this video format and go ahead and pause whenever you need to go over material, to write things down, or you can even rewind if you need to hear something a second time. All right, let's go ahead and get started. So first off, a quick overview of what we're doing today. We're going to start by talking about covalent and acid nomenclature. So we'll wrap up our naming and formula writing. And then we're going to take a look at covalent Lewis dot structures. At the end of this video, I'll talk about what exactly you should expect on your quiz. So if you're wondering about that, that'll come at the end of our video. Hopefully this instruction is helpful to you. As a reminder, I'm not going to be on campus the rest of this week. So if you do have questions, go ahead and shoot me an email, and I'll do my best to answer them when I can. So we're going to start off today with a review of naming ionic compounds. So go ahead and hit pause, record these substances in your notebook, and see if you can come up with the correct formulas. So again, pause, see what you can do, and then come back to check your answers. All right, let's see how you did. So starting off, we've got sodium and chlorine, so that's going to become sodium chloride. Next up, we have strontium and fluorine, that becomes strontium fluoride. Then we have ammonium oxide, that's one of our polyatomics that you're supposed to know. Then we have copper chloride. Now remember that copper is a transition metal. So we actually have to do something a little special with copper. We need to put a Roman numeral to indicate its charge. In this case, it's +2. And we know that it's +2 because it's paired with 2 chloride ions, each of which are -1. All right, next up, we have, this one's a challenging one. So this next one is actually an acid, and we'll talk in a few minutes about how to actually name this one. We know it's an acid because it starts with hydrogen. So this is actually going to be called phosphoric acid. And again, we'll talk about the rules for that in a few minutes. Next up, we have potassium hydroxide. And then we're going to end with another substance with the polyatomic, calcium sulfate. Right, and here are those answers typed out if you want to see that typed out. We're going to talk a little bit more about the transition metal as well as the acid, but the rest of those you should have been able to name based on your understanding of ionic compounds and polyatomics. All right, so let's go ahead and talk about those transition metals. So transition metals, they can have more than one charge. Often they're +2, but it actually can vary a little bit depending on the metal. So when we write the name of a transition metal in a formula, we actually include the charge or the oxidation state in parentheses after the name. So for example, copper +2 is known as the copper 2 ion. Notice that we write it in Roman numerals, and also that there's no space between the name of the element and the parentheses. This next one is going to be iron 3. Remember, the most common charge, with a couple of exceptions, for transition metals is +2. You should assume that it's +2 if not indicated. There are a couple of exceptions. The two big ones are going to be silver, which is generally +1. And then you have zinc and cadmium, which are almost always +2. So those three elements do not get Roman numerals. So it's important that you know those three elements. We also have what are called covalent molecules. Remember that covalent molecules are going to show bonding between two or more non-metal atoms. So when you're naming a covalent molecule, you're going to put the atoms in order from left to right on the periodic table. So least electronegative to most. And then you're going to change the second ending of the element to "ide," just like you would in an ionic compound. Then we're going to add these prefixes to show how many of each particular atom we're dealing with. It's important to note that mono is only used with the second element. So in this first substance, we've got carbon tetrafluoride. Now, the fact that carbon doesn't have a prefix tells me I'm dealing with just a single carbon atom. So that's going to be carbon. And then fluoride, that's going to be fluorine. And I've got the prefix tetra. Tetra means 4. So this formula is going to be CF4. My next example, I've got the formula and I need to come up with the name. So I'm going to start with hydrogen. I have 2 hydrogen atoms. So this is dihydrogen. And then I have a single sulfur atom. This is going to be monosulfide. Remember, we only use that prefix mono if we're dealing with the first element in a compound. Carbon monoxide is a good example of that. So carbon doesn't have a prefix, even though it's just one carbon atom. It's the first element, so we're going to leave mono off. However, we have monoxide, and that's a single oxygen atom. So we do need to include that in our formula. Our last example, you might have thought of as dihydrogen monoxide. And it's okay if that idea popped into your head, but what I really want you to recognize this as is just good old, plain old water. We're going to be using it a lot in chemistry. All right, next up, we're going to be talking about different types of acids. The first kind is known as a monatomic acid. Monatomic acids are going to be hydrogen plus one other element. The exception, of course, being with cyanide, which is a polyatomic that has a -1 charge. For monatomic anions that contain an acid, you're going to add the prefix hydro and change the ending to ic. So, for example, if we had hydrogen plus chlorine, that would become hydrochloric acid. We can also have acids that contain polyatomic ions. When you name something that has a polyatomic ion in it as an acid, then you're looking at the ending of that polyatomic name. So polyatomics that end in ate become ic, and polyatomics that end in ite become ous. The memory trick that I learned in school to help me with this was I ate something icky, and all night, gotta be a little creative with the spelling of night, I was nauseous. Hopefully that's helpful to you in preparing for quizzes. All right, so here's a little more practice for you. This is centered around naming acids specifically. So remember, your first step is to figure out, are you dealing with a monatomic acid or a ternary acid, an acid that has a polyatomic in it? If it's got a polyatomic in it, make sure you've got your polyatomic chart handy so that you can name it properly. Go ahead and hit pause, and when you're ready to check your answers, you can resume the video. All right, I hope you hit pause. Here are the answers when you're ready. Notice that hydrofluoric acid, that's a monatomic acid. So that one has a name that's a little bit different. Before we move on, I want to make sure you're all aware of the extra resources for nomenclature practice. Nomenclature takes a lot of practice. It's kind of like your multiplication tables. You have to practice just a little bit every day to really get good at nomenclature. The page linked below is a great resource for extra practice. It even lets you mix and match different types of substances for your practice. Okay, so in the past we talked about ionic bonding and how we can illustrate ionic bonds. Today we're going to talk a little bit more about covalent bonding and how we represent covalent bonds as a Lewis structure. Not all atoms are electronegative enough to steal electrons from other atoms. So instead, they're going to share those electrons. This results in what's known as a covalent bond, where those two electrons are being shared between two atoms. It occurs if the difference in electronegativity is less than about 1.7. To identify it is covalent bonding generally happens between two non-metals. Let's take just a quick moment to talk about network covalent substances. So, unlike molecular covalent substances, network covalent molecules have a network of bonded molecules. So, you can see in our illustration here that we've got a whole network of bonds between a whole lot of different covalent particles. By comparison, a molecular covalent bond is going to show just bonds between individual atoms within a molecule instead of a big system. There are two main types of network covalent substances. There's amorphous solids, which means they have an irregular shape and they're not a nice, pretty lattice structure, kind of like silicon carbide here. And then there's crystalline structures like graphite or diamond. Those structures are a lot stronger because they've got that bonding in many, many different directions. Atoms that show covalent bonding still want to fulfill their octet, but instead of transferring electrons from one atom to another, they're going to share those electrons and form a covalent bond. Each bond represents two electrons, so you count that for both atoms. And then you need to make sure that you include our unbonded pairs as well. So for example, we've got a fluorine bond here. That's two electrons. And then each individual fluorine atom has a total of 6 electrons that are part of what we call lone pairs, also known as unbonded pairs, or pairs of electrons that are not involved in bonding. There are a couple of atoms that don't actually need 8 electrons to be satisfied, so they don't follow the octet rule. The first is going to be hydrogen. Hydrogen only needs 2 electrons to reach its full valence shell, because it's in that first energy level that can only hold 2 electrons. Boron is kind of a special exception. Boron only needs 6 electrons to be considered full. It does not need a total of 8. These 3 problems are example problems from your simple Lewis structures and covalent nomenclature problems. Let's go ahead and work through these together. So your first step is going to be to draw the Lewis dot structures for each element. Right away, I can tell we're going to have a single bond formed here because hydrogen needs to share that 1 electron and bromine's got an electron to share as well. So when I draw my ionic Lewis dot structure, I'm going to show a bond connecting hydrogen and bromine, and then I'm going to add those lone pairs on bromine. That's it. Our next example is iodine and bromine. So we already know that bromine's got 7 valence electrons. Iodine is actually in the same group as bromine. It also has 7 valence electrons. So I'm going to form a bond with those 2 electrons that are by themselves. And there's our ionic compound. Covalent compound, sorry. All right, our last one is going to be with 2 chlorine atoms. So chlorine, also group 7 atom. So chlorine is also going to form a single bond. In this case, it's just going to be with itself. So I've got a single bond with 2 chlorine atoms, and each of those has 6 valence electrons. It's also important to talk about our double and triple bonds. Double bonds form when we share 2 pairs of electrons between atoms. Triple bonds form when we share 3 pairs of electrons between atoms. Let's talk about some tips for drawing Lewis structures. First off, the least electronegative atom is usually the central atom. That means all of the other atoms are going to be bonded to it. Generally speaking, that's actually going to mean carbon. If you don't have carbon in your compound, then it's going to be whatever element is furthest to the left on the periodic table. To draw a Lewis structure, you're going to start by using the number of unpaired electrons as a guideline for how many bonds that atom's going to form. For example, carbon has 4 unpaired electrons. That means it's going to form 4 bonds. Oxygen, by contrast, has only 2 unpaired electrons. Oxygen generally is only going to form 2 bonds. If you're still stuck and having trouble figuring these out after doing a couple practice problems, go ahead and check out the nasal method. You should be able to find this on Google, and it's also linked in our Unit 2 resources page. We also need to make sure to talk about ions. So to make a Lewis structure for an ion, you're going to add an electron if the ion is negative, or subtract an electron if the ion is positive, based on the charge, and you're going to take away the appropriate number of electrons. For example, ammonium has a +1 charge. That means that I need to take away 1 electron. So if I have 5 electrons from nitrogen and 4 electrons from hydrogen, 1 from each of those hydrogen atoms, that puts me at 9 electrons. But since this has a +1 charge, that actually is 8 electrons, which works out really well because that's going to help me figure out the structure of my molecule. So there I've got all 4 of my bonds accounted for. That's good. And I've got all 8 electrons accounted for as well. My last step is going to be to put a bracket around this and add the charge to indicate that it's a charged particle. All right, time for some more examples. So I want you to complete the remainder of the problems on that first practice sheet. When you're done, come back here to check your work. On the next slide, I'll have an answer key available for you. But don't do that until you've had a chance to try it out and check your work yourself. All right, here are the solutions for the other 9 problems on that sample set of problems that you got in class. Go ahead and take a moment to check your answers. And if there are any problems you're unsure of, go ahead and talk with your table group to see if you can figure out where you went wrong. All right, at this point, we've officially covered everything that's going to be on your quiz for next class. So everything after this is going to be stuff that shows up on your quiz next week. Try not to panic too much. We're going to talk first about a concept called resonance. And what I want you to do in order for us to talk about resonance is I want you to draw the Lewis structure for nitrate, NO3-. Go ahead, hit pause, take a moment, and draw your structure for nitrate. Okay, so you came up with one of these three possible options for your structure of nitrate, hopefully. Now, the question is, which one of these is actually the right answer? What makes one particular oxygen atom more special than others? Like, why does one specific oxygen atom get a double bond? Truth is, nothing makes it more special. So each one of those oxygen atoms is just as likely as the others to form the double bond. The double-headed arrow indicates what's known as a resonance structure. So that means that those electrons are transferred into a bond versus a lone pair pretty easily. When we look at what's actually going on, it's important that we remember that these bonds are really just where electrons are commonly found. So when we talk about these partial bonds, right, or these double bonds or triple bonds in a resonance structure, what's really going on is those individual bonds they're stronger than a single bond. They're a little bit shorter than a single bond, but not as strong as a double bond. It's like 1 1/3. The charge on those oxygen atoms is not neutral, but it's not a full -1 charge either. In this particular case, it's going to be approximately -2/3. Again, this is what we see specifically for resonance structures. I'm going to take a moment to teach you a tool that you can use to help you evaluate your Lewis structures, and that's something called formal charge. So formal charge is used to assign the charge on individual atoms within a compound. To calculate the formal charge for a particular atom, you're going to take all the lone pairs and half of the shared electrons, and you're going to add all of that up. Then you're going to subtract the number of electrons that the neutral atom would have. The sum of those formal charges must add up to the total charge. So those formal charges that we calculated in that first step, you have to add up to the total charge. This is a good tool for figuring out the most probable Lewis structure. I'm not going to ask you a specific question where I say, label the formal charges for these atoms. I'm not going to ask you to do that. But you might have a Lewis structure problem where you have to draw out the formal charges in order to help you figure out what the right answer is. So here's an example of formal charges where we have what we call non-equivalent Lewis structures. That just means that that particular structure is not a mirror image, that it could be either or. And so we're going to use formal charges to help us identify which one of these structures is the right choice. The one where the formal charges is closest to 0 is the correct one. It's the one that's going to be favored. So this is considered the correct structure, the actual structure of carbon dioxide. Notice that each one of those atoms has an overall 0 formal charge. If you can't have all zeros in your structure, then your next choice is going to be to put the negative formal charge on the more electronegative atom. That means farther to the right side of the periodic table. In this case, we've got a -1 charge on sulfur on the left side, and on the right side, we've got a -1 charge for nitrogen. Nitrogen is the more electronegative atom, so that's the atom that should be carrying a negative. All right, it's time for some more practice. So take a look at the worksheet that's titled Multiple Bonds and Resonance Structures, and we're going to work through some problems together. So this first one, I've got hydrocyanic acid. All right, so I've got hydrogen with 1 valence electron. I've got carbon with 4 valence electrons. And then I've got nitrogen with 5 valence electrons. All right, and it's my job to figure out how to bond these together. The first thing that I need to recognize is that my carbon atom That's the least electronegative besides hydrogen. Hydrogen can't be a central atom because it can only form one bond. So we're going to stick with carbon as our central atom. And I know that I'm going to have one bond that connects carbon to hydrogen. From there, though, I have 3 different lone electrons that I have to deal with. Coincidentally, nitrogen also has 3 lone electrons. So what we're going to see is that's going to form a triple bond, leaving nitrogen with a single lone pair. You've actually already seen an example of carbon monoxide, but let's go ahead and work that one out. So I've got 4 electrons for carbon, and for oxygen, I've got a total of 6 electrons, 2 of which are going to get involved in bonding. So I'm going to form a double bond between carbon and oxygen. That takes care of those extra electrons. And then my lone pairs get added to each atom. My last example is with acetate. So I'm going to start by identifying this carbon as my central atom. And I've got 2 different oxygen atoms connected to it. All right, so there's the first part of my structure. Then it also says I'm going to have a CH3 attracted to it. So I've got another carbon, another hydrogen, 3 hydrogens in total. My last step, since this has a charge on it, is to put brackets around it. So this should be a -1 charge. I also want to go ahead and actually check my math and make sure that I have the right number of electrons. So remember, each hydrogen atom has 1 electron. So that's 3 electrons total. Then my carbon atoms, I have 2 carbon atoms with 4 electrons. So that's going to be 8 electrons total. I have 2 oxygen atoms, each with 2 bonding electrons, but a total of 6 electrons. So I've got quite a bit to work with. When I go through and I count all my electrons, I should end up with 23 electrons. But notice I also have that negative sign with acetate. So that actually is 24 electrons. So if I count, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's exactly what I need. So my structures here are correct. The only thing that I need to add for acetate is one of those resonance structures, because that double bond can form between either one of those oxygen atoms. All right, and so there's another example of our ionic substance. I'm going to draw my double-sided arrow to show that that's resonance, and we're good to go. All right, so now I want you to go ahead and pause again and see if you can work through the multiple bonds and resonance structures worksheet. Remember, you don't have to do every single problem. You're welcome to do odd-numbered problems or even every 3rd problem. But I do want you to come back here to check your work, and if you find you're struggling, maybe spend a little more time on practice problems. Here are some of the answers to that practice set. Notice that we've got an exception here in nitrogen dioxide. So nitrogen dioxide has a 1 weird electron that kind of just hangs out. We call that a free radical, so it's an electron that's unpaired. It's one of our weird exceptions. Here are a few more answers. Again, go ahead and take a couple minutes to check your work. Oh, and I see here that my resonance structure for benzene is not correct. So I'm going to go ahead and fix that real quick. my benzene molecule wasn't showing the double bonds in the right spot. It was showing identical double bonds. There we go, much better. Notice that for nitrate, I've got that negative sign for each one of those ionic molecules. All right. There are some other types of molecules that show resonance. We just looked at benzene, that's a good example. We also looked at acetate, again, another good example. There are a couple of other classic examples, including ozone, which is O3, and sulfur tetroxide, which is sulfur with 4 oxygen atoms bonded to it. Sulfur tetroxide is one of those weird exceptions. It can actually form a total of 6 bonds, which gives us a total of 12 valence electrons to work with, potentially if it's got electrons from the right donor. Okay, so here are a few more examples, and each one of these shows an exception or breaks a rule for covalent Lewis structures. Go ahead and hit pause here and see if you can draw the correct structures for these 3 exceptions. All right, let's see what you came up with. Here are the correct structures for those 3 substances. So we've got our nitrogen dioxide molecule here, which again shows that weird little electron that's floating around as a free radical. We've got our xenon difluoride. This one's a weird one because it's going to have a total of 5 pairs of electrons or 10 valence electrons bonded to xenon. And then we see another example of sulfur where we've got those 12 valence electrons or 6 pairs of valence electrons attracted to it. All of these are good examples of exceptions. Basically, when you're drawing a covalent structure, if you can't work it out using our normal rules, then you start looking at exceptions. Sulfur is a great example of an atom that frequently shows exceptions. And then xenon and other noble gases are going to show similar patterns as well. So your last step is going to be to work through some of the rule breaker Lewis structures in the practice set. Once you've had a chance to try some out, you're going to come back here to check your work. Again, remember, you don't have to do every single problem on that rule breaker sheet. You're welcome to just do a few of them and come back to see where you're at. All right, here are the correct answers for the rule breakers on your worksheet. Here are some more answers. Hopefully that practice was helpful to you. Your homework today is going to be to work on the giant nomenclature practice. And then if there's any covalent Lewis dot structure practice that you need to finish, to go ahead and wrap up on that. Remember, you don't have to do every single problem. The same is also true of that giant nomenclature practice. In fact, I suggest for that nomenclature practice, you do odd numbers only. There's an answer key posted in Schoology for you when you're ready to check. And then make sure that you're ready for your quiz next time. That includes classifying ionic and covalent and acid substances, using nomenclature, and being able to draw Lewis structures for some simple covalent compounds, as well as talk about properties of different types of bonds. All right, happy studying. Good luck with your quiz next class, and I'll see you all next week.